So, hello everyone. Good night, maybe good morning, and also good afternoon. So, my name is Cheng Gu. I'm a professor in school environment at Nankai University. So, today is our second lecture for the IAS Microplastics series, webinar series. So, today we have our speaker is from Nankai University, Professor Lei Wang. Because he has a class today, so he pre-record today's lecture. And but later on, he will join us to, if you have any questions, Professor Wang can answer your question. Okay? So for the beginning, I would like just to give a very brief introduction of Professor Wang Lei. Professor Wang is a professor in Nankai University in China. He's also the head of the Department of Environmental Science in Nankai University, and also Deputy Director of the Key Laboratory of Environmental Pollution Processes and Benchmarks under the Ministry of Education. His main research area is the environmental behavior and exposure of new pollutants. Currently, he has already hosted over 20 national key research and development projects, and also some other scientific research projects, and also published over 100 ICI papers and obtained the C authorized invention patents. He served as the Deputy Editor-in-Chief of Eco, Environment and Health, and also Bulletin of Environmental Contamination and Toxicology. He's also the editorial board member of Ecotoxicology and Environmental Safety. He's a member of the Microplastics working group of the Chinese Soil Society. All right, so we can start his lecture. So I will share my screen.
Hi everyone.
So it's okay?
Morning,
everybody can hear?
Good evening.
Can hear and see the
PPT. Environmental Science and Engineering at.
Is that okay?
That's good. I would say just turn it up a bit.
Okay, right? So I will continue then. All right. It's a bit quiet. Okay.
Hi everyone. Good morning, good afternoon, good evening. This is Lei Wang from the College of Environmental Science and Engineering at Nankai University. I'm very honored to have the opportunity to talk something on the detection method of microplastics and our research on its ecological risk. The content in this report mainly comes from the research of our team, but also includes some research results from other peers. This presentation has 4 sections. It's about methods for separation and the detection of environmental microplastics. Before I introduce the microplastics, I'd like to say that plastic is a kind of great material. Plastics are widely used in the industrial processing and production and daily life, such as packaging, construction, transport, electronic, agriculture, and so on. Due to their lightweight chemical stability, corrosion resistance, easy modeling, and low processing cost, they play a very important role in social development. According to the statistics, the global annual plastic production has exceeded 350 million tons, of which only 6% to 26% of plastic waste is recycled, and as much as 94% of plastic waste is eventually discharged into the environment through various channels. Plastic debris in the environment can migrate over long distance through external forces such as rivers, ocean currents, and wind. It has been reported that plastic debris pollution currently existed in deep seas and the polar regions. Plastic entering the environment will decompose into tiny plastic fragments or particles due to long-term physical and chemical effects. When their diameter is less than 5 millimeter, they are defined as microplastics. In the natural environment, microplastic will further decompose to form nanoplastic with a size less than 1,000 nanometer. In recent years, more and more attention has been paid to the pollution of microplastics. At the first United Nations Environmental Assembly, it was also proposed that special attention should be paid to marine microplastic pollution. At the second United Nations Environmental Assembly, microplastic pollution was listed as an important scientific issue in the field of environmental and ecological science, and has become a major global environmental issue alongside global climate change, ozone depletion, and ocean acidification. However, so far, there are still many problems in the detection of microplastics, and the detection method of microplastics urgently needed to be standardized. Now we return to the detection of microplastic. If the composition of the plastic is known, its analysis can be performed by optical or electronic microscopy. As shown in the figure, scanning electron microscopy, atomic force microscopy, and optical microscopy are used to test and analyze the microplastics. Even the plastic particles we actively add that are ingested by plants or animals can be observed. This page demonstrates that analysis and testing of microplastics using confocal laser scanning microscopy and fluorescence microscopy. By using fluorescence signals, we can identify these particles. The combination of spectroscopy and macroscopy imaging technology is gaining more and more attention in the detection of microplastics. The combination of these two methods allows researchers to observe the morphology of microplastics and identify the type of polymers at the same time. An article published in 2018 used macro FTIR to analyze the appearance and the type distribution of microplastics detected at different treatment stages in sewage treatment plants. FTIR microscopy is commonly suitable for samples below 100 micrometer, and the minimum diffraction limit can be detected is 10 micrometer. Another article published in 2019 used the macro-Raman spectroscopy technology to explore the type and the concentration of microplastics in atmospheric deposition in urban Hamburg. By using confocal microscopy Raman technology, people can even successfully identify different types of nanoplastics. Raman enhanced material that can significantly enhance the Raman signals. The bottled water can be analyzed directly after filtration with 100 nanometer filters without any further treatment. However, the method selectivity is poor because this method doesn't analyze the individual particles. So if there are multiple types of particles coexisting, this method cannot work. Compared with the analysis of those microplastics with known components, the testing and the analysis of environmental microplastics in the real environmental samples is much more complicated. For example, you can see many suspected microplastic particles in the dust, but identifying their composition is very difficult. When you are lucky, the results are like the picture shown on the left. The spectrum of the tested particles is very similar to the standard spectrum of polymer. Therefore, it is easy to identify the type of plastic polymers being tested. But in most cases, as shown in the picture on the right, the results obtained are specious and difficult to judge accurately. The samples will be digested before the separation by using biological or chemical digestion. The figures showed different digestion methods. However, some environmental metrics are difficult to be digested. In addition, the digestion process will also affect the microplastics themselves. For example, some plastics are not acid or basic resistant, and some are easy to oxidize. Plastic may even break during digestion. This will also cause misdetection of number detection of microplastics. After digestion, flotation for microplastic is required. The most common method is density separation. Different types of microplastics have different densities. Therefore, the flotation solution will affect the separation efficiency of microplastics. In theory, environmental microplastic particles can be floated out by many salt solutions. But can they really be floated out? Tested the efficiency of commonly used flotation separation method. LC mass was used to measure the mass concentration of microplastics in the floated part and the residue part of soil samples collected in landfill site, and the efficiency of the classic flotation method was evaluated. It was found that 30% to 70% of PET polymers in the environmental samples were missed. Therefore, it is difficult to completely separate the microplastics from the environmental samples through the flotation process alone. Due to environmental aging, it is difficult for us to achieve an ideal recovery rate for environmental microplastics. Therefore, we attempt to change the detection method to avoid sample pretreatment. We consider it mass spectrometry detection technology. Mass spectrometry detection technology, such as pyrolysis gas chromatography, has been commonly used in microplastic detection. This method pyrolyzes polymers into small molecular fragments and calculated the concentration of microplastic polymers through the concentration of the fragments. However, due to the lack of selectivity in fragments, this method still needs to separate the microplastic in advance. PET, also known as polyester plastic, is widely used in fiber production and drinking bottles and packaging materials, with a global annual production of 87 million tons. PC is one of 5 types of the most important engineering plastics, which are widely used in our daily lives, such as plastic cups, and mobile phone cases. The global annual production of PC is 6 million tons. PC can be depolymerized to bisphenol A. Accordingly, the amount of PET and PC polymers can be calculated. Concentration of PA polymers. PA is also a commonly used plastic. The most common are two kinds of PA6 and PA66. Their main purpose is to make synthetic fibers. The global annual production is 3.4 and 4.4 million tons respectively. Out easily degradable plastic polymers. In recent years, many degradable plastics have gradually entered our life, such as polylactic acid, PLA. The annual global production of PLA in 2020 is 0.33 million tons. It is mainly used in the fields of food packaging, methodical treatment, and 3D printing. The structural formula of PLA is shown in the figure. Detected by LC mass after extraction. Therefore, mass concentration of PLA polymers can also be detected by the mass spectrometric method. Area, port area, tourist area, and control area, and compared the differences in quantity abundance and quality concentrations. Although the abundance of microplastics in port area and tourist area is significantly higher than that in the protected area, there is little difference in their PET and PC mass concentrations. This suggests that small particle size microplastics with significant contributions might be overlooked by macro FTIR technology. We also investigated the distribution of microplastics in indoor and outdoor dust in major cities of China, and found that PET microplastics can be detected in all dust samples with a maximum concentration of 120,000 microgram per kilogram. PC polymers can be detected in about 70% of the dust samples. The concentration of PC is up to 107 microgram per kilogram. The concentration of PET microplastics in indoor dust was significantly higher than that in the outdoor dust. We also cooperate with Professor Cannon from the United States to measure PET and PC polymers in the indoor dust of 12 countries around the world. PET microplastics can be detected in all dust samples, and the detection rate of PC polymers is more than 99%. Whether in China or global, the concentration of microplastics is significantly positively correlated with the local GDP and population density, indicating that the level of human activity is an important factor in microplastic pollution. We also analyzed the PA plastic polymers in dust. PA6 and PA66 microplastic polymers were detected in all the indoor and outdoor dust samples with the maximum concentration of more than 1,000 microgram per kilogram. Through the analysis of atmospheric dustfall in Tianjin, China, it is found that PET polymers are also widely distributed in dustfall with a maximum concentration of 5,400 microgram per kilogram. According to the concentration of PET polymers in the dustfall, it is estimated that about 5 to 30 tons of PET polymers entering the terrestrial environment through dustfall every year. Through the detection of PET polymers in the sludge of major sewage plants in Tianjin, it was found that sludge recycling and fertilization resulted in 30 to 50 tons of PET polymers entering the terrestrial environment every year. In addition, the mineralized soil of the landfill is mostly used for urban landscaping, and PET polymers also exist in mineralized soil of a landfill. Thus, the amount of PET polymers imported into environment through the utilization of mineralized waste soil in China can reach tens of thousands of tons every year. We tried to construct a correlation between the mass concentration and the quantitative abundance of microplastics. We compared the result of microplastic concentration obtained by the two technologies. The results showed a positive correlation between the concentration of PET and the abundance of total microplastic fibers, indicating that PET polymers is a good marker for microplastics in wastewater. And finally, through the mass concentration of PET and the quantitative abundance of microplastic fiber, we constructed a standard plastic fiber with a length of 600 micrometer and a diameter of 50 micrometer. In addition, we also analyzed and tested microplastics in sludge from sewage plant in Tianjin and microplastics in sludge from sewage plant across the United States. Combining the discharge of sewage and sludge and the amount of the sludge used, we evaluated the flux of microplastics through sewage and the sludge discharge into the environment. The results show that although sewage treatment plants are a very important sink for microplastics, they are also an important source of microplastic emission. The last session is on the studies of the electrical and the health risk of microplastic. Dust is a very important pathway for human exposure to pollutants. The exposure of microplastic through dust in people of different age groups was assessed according to the concentration of PET and PC microplastic polymers in dust, and the daily intake of dust was estimated. The result found that the average daily exposure to PET among adult men in our country is about 6,500 nanogram per kilogram body weight per day. The daily exposure of infant to PET can be as high as 150,000 nanogram per kilogram body weight per day. It shows that microplastic in dust pose a high risk of exposure to infant. One of the reasons is that the babies also lick their hands and toes, and their dust ingestion is very high. This is a study of microplastic in human feces with a small sample size. It is found that PET microplastics in infant feces are significantly higher than those in adults, but the concentration levels of PC microplastics are similar. The daily exposure level of infants and adults to microplastic was assessed based on the concentration of microplastics in feces, and it was found that the daily exposure levels of infants to both PET and PC microplastics were higher than those of adults. Some studies have reported that the presence of microplastics in the human placenta. The presence of microplastic in mechanism in this study further proved that plastic polymers can break through the placenta and enter the unborn baby. The exposure of infants to microplastics requires more attention. In addition, we also did a study on pets related to the exposure to microplastics. Because pets, especially cats and dogs, live in the same environment as humans, they are often used as exposure monitoring species for indoor pollutants. Microplastics are mainly excreted from the gut as particulate matter. Therefore, we collected food and facial samples from cats and dogs for microplastic analysis. Monitoring found similar distribution of the two types of microplastics in pet food for cats and dogs. The concentration of PET microplastics in cat feces was higher than those in dog feces, and there were no significant difference in PC microplastics. This suggests that not diet but dust ingestion is a significant source of microplastics exposure in cats. Using the mass spectrometry detection method developed by our group, the excretion patterns of macro or nanoplastics of different shapes and sizes in rats were quantitatively explored. The infected feet was fed only on the first day, and the feces, urine, and blood was collected for 7 days. Research have found that small particles of microplastics have a much longer intestinal retention time than the large particles. The detection of polymers in the blood of rats indicated that microplastics posed a risk of intestinal absorption. In the zebrafish fiddling experiment on macro-sized PET and PLA plastics, PET and PLA were continuously ingested during the first 5 days of fiddling and had the highest intake on the 5th day. During the elimination process in the last 5 days, 90% of them are extracted on the first day, and almost all of them can be extracted in the remaining 4 days. However, the intake of the two plastics is very different. It was found that zebrafish can recognize and ingest dove containing lactic acid. PLA is 170 times more than PET, indicating that zebrafish are more willing to ingest the PLA compared to PET. This may be related to lactic acid, the degradation of PLA. Lactic acid is one of the nutrients for fish. The earthworm approach and avoidance tests were conducted in a chamber which was divided into 4 zones by glass panels, including zone A, B, C, and D, spiked with different microplastic polymers. After 2 days' experiment, the earthworms showed a significant approach avoidance behavior in the 4-compartment experiment. The earthworms in a starvation state showed an obvious approach to PET and PLA microplastic. More earthworms moved to areas packed with PET or PLA microplastics, especially in the starvation state. This may be due to their preference for free monomers in PET and PLA, that is, PTA and lactic acid. Others are potential cause for earthworms to select food. As microplastic polymers larger than 0.8 micrometer in earthworm cast can be separated and observed, the extracted macro PET and PLA particles, which were divided into 2 particle sizes, that is, the original size and the smaller size, were counted respectively. In the cast collected on the first day after exposure, a great number of PET particles can be observed. During the 10 days excretion, the proportion of smaller PET particles in PET microplastics separated from the cast increased from 14% on the first day to 30% on the 10th day. Differently, the smaller PLA particles in the cast of the first day accounted for 45% of the PLA microplastic, and the proportion further increased to about 70% on the 10th day. The digestive tract of the earthworms seemed to be more effective in breaking PLA polymers. Although submicron and nanocron particles were hard to be identified by the microscopy, their occurrence could be measured by LC mass. In comparison to the mean concentration of macroscopically recognizable PET in the cast during the 10 days excretion, the amount of the submicro and nanocron PET polymers were much lower. Differently, the mean concentration of submicro PLA were even higher than that of the macroscopically recognizable PLA. This verified that PLA in earthworms is more likely to break down than PET, and a large number of smaller-sized PLA particles might be formed and released by earthworms. Without considering the particle size distribution, excretion of PET and PLA in earthworms could be well described by the first-order kinetics, according to the total mass of polymers in the earthworm casts. The elimination rate constant for PET and PLA in earthworms could be calculated, which indicated that PET microplastic were eliminated more quickly than PLA. Plastic is the general term for artificial polymers. In addition, there are many non-artificial polymers in nature. The ecological risk difference between them still need to be identified. The ecological and health risk of plastic polymers are still controversial, but plastic, an artificial organic carbon, is constantly accumulating on the Earth's surface, making it at least an emerging geological material that cannot be ignored. Some new ecological risks of polymers have also been continuously discovered. For example, plastic particles can block membrane pore and cause hypoxia in fish embryo. Plastic surface biofilms may carry more pathogenic bacteria and resistance genes. Therefore, overall, the ecological risk of microplastic demands continuous research. That's all for my presentation. Thanks for the contribution of the cooperators, and thanks for your attention.
Okay, so thank you, Professor Wang. Actually, he has already arrived in the conference, so he can answer question. When you have any question, you can ask. I think it's a very interesting, like presentation, because the analysis of this microplastic is still a big problem, I think. Right, so there's a very good research to doing something about the the microplastic. So any questions? So Doc, you mute.
My apologies. Thank you. I have a question for you, Professor Wang. Given the problems in the flotation technique and separation and so on, ultimately, do you think that mass spectrometry is going to be the solution to accurate measurement of plastics, or do you think we need to look for an entirely different approach?
Thank you, Professor. First, I will say sorry. Can you hear me? Hi.
Yeah. Yes, we can hear you.
Yes. Okay. First, I want to say sorry to everyone because I found that the video doesn't work well. I just finished another class and go back to my office. And for the question, I think yes, there's I found that there's a big problem for the flotation efficiency of the microplastic because of the environmental aging process, I think. The problem is when we spike the standard particles of microplastic to the samples, we always can obtain the ideal recovery efficiency. But for the real aged microplastics, we tested by the LC-mass, we can find that in the residues, there's still many microplastic residues. So we try to develop some method to directly analyze the whole samples without pre-treatment. But unfortunately, we cannot do that for all the polymers in all the samples. But sometimes we have to separate the particles from the samples. So yes, for some polymers, in some cases, it is a good method to use LC-mass to directly analyze the whole sample so that we can avoid the effect of the flotation recovery efficiency. But in other cases, I think we have to find some other method, or we just improve the separation method.
So, Professor Wang, I may ask you a question about regarding like the because we are doing the exposure to the earthworm, right, for the PET and PLA. So when I look at your presentation, you said like they can be so both of the microplastic can be created by the earthworm, right? So do you think there are some digestion process or some other like the changes on the surface of this microplastic? Is that anything like the surface functional groups will change, or is that did you do some research?
Yeah. Yes. Maybe there's some. I think it must have some change happened on the surface of the microplastics, but it is somewhat difficult to detect it because we focus on the very tiny particles, and they cannot observed by the scope. So we use mass spectrum to detect it. So the surface group is very on the surface is very difficult to detect. But I think it must happen. And when the earthworms or fish ingested the particles and digested them, some of the polymers may decompose, and some oligomers occurred. Yes, it's a trust.
Thank you. So any other questions from the audience?
I was also interested in your data on babies compared to adults and the concentrations that were found in terms of, excuse me, some of the plastics. Is it just a matter of the, like the food sources, or is it the feeding mechanisms? What do you account for the differences?
I think the difference is mainly due to the indoor dust. because for the similar difference between the cats and the dogs are also observed in another study. Because the infant has ability to injection many indoor dust because they cannot stopping how to say it just intake many indoor dust from the such as fibers, just like a cat. It's different to dogs because cat intake much more dust than dogs, so we can find more microplastics polymers in their feces. And for the food of cat and dog, we detected the concentration of different polymers in the food of pets and found there's a little difference found between the different food of pets. And for the food of children and adults, we also measured the polymer concentration in different food. And for the packaging food, the polymers concentration is somewhat higher than the fresh food, but no significant difference can be observed between the infant food and the food of adults. And yes.
So any other questions? So yeah, if we have no questions, so we can just stop today. Thank you very much, Professor Wang. Very yeah, we can discuss. If you have any other questions, the audience, you can always contact with Professor Wang. And also, I would like to introduce for next week the same the webinar. It will be from Professor Denise Metronol. He's a professor from ETH Zurich. He'll talk about the challenges and opportunities for marine nano and microplastics in the complex environmental systems. So we will have the same time, and also through the the webinar for next Wednesday, the same time.
And yeah, thank you, Chen. And just before we end for today, I just also want to once again mention that we have upcoming in December the IIES Science and Policy Workshop. It will be held in Santiago, Chile. And I would invite any of you who are interested in joining us there to go to our website where you can find out more details. We will be having a session on microplastics at that meeting, so I hope that some of you will be able to join us. And for any graduate students who are with us today, I would also have you look at our website for the International Graduate Forum, which will also take place in Chile following that workshop. It'll be in a city called Puerto Montt in Chile. So please take the time to explore our website, and as I said, hopefully some of you will be able to join us at those meetings. Thank you.
Okay, thanks, Doc. Okay, see you next week, and we'll continue our webinar about the microplastics theories. Thank you.